everything around us. This pen, this notebook, even the air that you breathe is made up of tiny building blocks called atoms. Yes, we've all heard about that before. But did you know that atoms can remix themselves to make different orbitals? Welcome to the world of hybrid atomic orbitals, where atoms mix their orbitals to make different bonds.
Hybridization is when atomic orbitals mix together to form new orbitals called hybrid orbitals. These orbitals explain the shapes and angles of bonds and molecules. They don't exist in single atoms, only when atoms bond to make molecules.
Valence bond theory predicts bonds, but sometimes it doesn't match the actual bond angles we observe. For example, in water, theory predicts a 90-degree angle, but in reality, it's 104.5 degrees. To fix this mismatch, scientists developed the concept of hybridization to explain the true shapes of molecules.
Water molecule, 90 degrees theory versus 104.5 degrees actual. Oxygen in water uses sp3 hybrid orbitals, not pure p orbitals. That's why the HOH angle is 104.5 degrees instead of 90 degrees. Hybridization adjusts orbital orientation to match the real molecular geometry.
The key features of hybrid orbitals. Number 1. Do not exist in isolated atoms. Number 2. Have new shapes or orientations. Number 3. The number of orbitals mixed is equal to the number of hybrid orbital forms. Number 4. All hybrid orbitals in a set are equal in shape and energy. Number 5. The type of hybridization depends on electron pair geometry, based on the VSEPR theory. Number 6. Hybrid orbitals form sigma bonds. Leftover orbitals form pi bonds.
Mix 1s plus 1pn, 2 sp orbitals. Geometry, linear 180 degrees. Example, BeCl2 or beryllium chloride, and CO2 or carbon dioxide. In sp hybridization, 1s and 1p orbital mix to form two linear orbitals. They point 180 degrees apart, forming a straight line structure. BeCl2 and CO2 are common examples.
Mix 1s and 2p combine to form 3sp2 orbitals. Geometry, trigonal planar, 120 degrees. Examples include borane and formaldehyde. sp2 hybridization makes three orbitals arranged 120 degrees apart in one plane. It explains flat, trigonal shapes like borane and formaldehyde. Atoms in double bonds, like in ethane, also use sp2 orbitals.
Mix 1s plus 3p gives 4 sp3 orbitals. Geometry, tetrahedral, 109.5 degrees. Examples, CH4 or methane, NH3, and H2O. Bond angles are smaller with lone pairs. NH3 is about 107 degrees and H2O is about 104.5 degrees. In sp3 hybridization, 1s and 3p orbitals combine to form 4 equal orbitals. They create a tetrahedral shape. As seen in methane, lone pairs in ammonia and water slightly reduce the bond angles, making them a bit smaller than 109.5 degrees.
Mix 1s, 3p, and 1d to combine 5sp3d orbitals. Geometry, trigonal bipyramidal, 90 degrees and 120 degrees. Examples include phosphorus pentachloride, sulfur tetrafluoride, and chlorine trifluoride. sp3d hybridization forms 5 orbitals with 2 bond angles, 90 degrees and 120 degrees. Phosphorus pentachloride is a typical example.
Mix 1s3p and 2d orbitals combine to form 6sp 3d2 hybrid orbitals. Geometry: octahedral 90 degrees. Example: SF6, xenon tetrafluoride and iodine pentafluoride. This type mixes 6 orbitals that point 90 degrees apart in all directions. It forms an octahedral geometry. Examples include sulfur hexafluoride, written as SF6, and xenon tetrafluoride, written as XeF4.
How to determine hybridization? First, draw the Lewis structure. Second, count regions of electron density, bonds, and lone pairs. Third, match geometry, assign hybridization. Keep in mind, 2 regions is sp, 3 is sp2, 4 is sp3, 5 is sp3d, and 6 is sp3d2.
So, in summary, hybridization explains why molecules look and behave the way they do. It connects quantum mechanics, bonding, and geometry in all in one idea. So, the next time you see water, methane, or even the air around you, remember, those atoms are mixing and matching their orbitals just to stay balanced.